Hello. Once again, my name is Brett Lucht, and this is my second lecture on lithium-ion batteries. Today's lecture will be primarily focused on electrolytes within lithium-ion batteries, and will be an overview of the general aspects of electrolytes and what makes good electrolytes for lithium-ion batteries. And what the advantages and disadvantages of different electrolyte formulations are. The following two lectures will be covering research that's been conducted in my laboratory on the reactions of the electrolyte with the surfaces of electrode materials, both the anode and the cathode, and the characterization of the interfacial films of these materials. So with that, we will move on. Okay, so thank you again for attending the lecture on electrolytes for lithium-ion batteries. So as we went over in the first lecture, the lithium-ion battery has three primary components, which are the cathode, which are typically lithiated metal oxides. Lithium cobalt oxide is the original cathode material that was developed by Professor Goodenough. However, most current lithium-ion batteries have similar layered cathode materials. However, they primarily contain either lithium nickel cobalt aluminum oxide, which is typically referred to as NCA, or lithium nickel manganese cobalt oxide, which is typically referred to as NMC or NCM cathode materials. The two other cathode materials that are pretty widely utilized in current lithium-ion batteries are lithium manganese oxide and lithium iron phosphate. These are both very good cathode materials for high power applications in particular. They're also lower cost. However, their energy densities are lower than the NMC and NCA materials. Two cathode materials that are currently receiving a lot of attention, which we'll see some more of in the following lectures, are lithium nickel manganese oxide, which is typically referred to as the high voltage spinel, and the lithium rich or the manganese rich high energy NCM, which is similar to the layered cathode materials, but has higher energy and higher voltage. But once again, both of these two materials, the high voltage spinel and the high energy NMC materials, have significant amounts of challenges and problems associated with them. On the anode side, as I already mentioned, the anode is primarily, most commercial lithium-ion batteries have anodes primarily composed of graphite. However, there are also in a lot of current lithium batteries, especially for consumer electronics devices, silicon graphite composite anodes, which contain small amounts of silicon, which significantly increases the capacity of the anode. There's still a lot of research in the development of silicon anodes for lithium-ion batteries. And of course, lithium metal is frequently referred to as the holy grail in terms of lithium-ion battery anode material, but there are many challenges associated with it, which we will go over the next few lectures. So going back to the primary focus of this talk, which is the electrolyte. So the electrolyte is a combination of a salt, lithium salt, which is then dissolved in some solvents to make the electrolyte formulation. The most frequently salts of interest include lithium hexafluorophosphate, LiPF6, which is the most widely utilized salt commercially for lithium-ion batteries. Two of the most recent lithium salts that have really become, I would say, high interest to the battery community are lithium FSI, LiFSI, and LiTFSI, which is lithium fluorosulfonyl imide, or bis fluorosulfonyl imide, and lithium TFSI, which is lithium bis trifluorosulfonyl imide. We'll go over some of these salts later. These are two of the more promising salts right now within the battery community. However, both of them have challenges and issues compared to LiPF6. Some of the older salts that have been investigated for long periods of time include LiBF4. LiBF4 is also an interesting salt. It has some advantages for high voltage applications, but it also has some problems associated with conductivity. Also, it has some problems with low temperature performance and more resistive interfaces. Lithium bisoxylato-borate, or LiBob, is another salt, along with half-bob, or lithium difluoroxylato-borate. Both of these salts have at times received a lot of interest within the community. Lithium bisoxylato-borate, LiBob, has problems in terms of solubility of the salt. Also, it has originally had some purification issues with it. It also has some problems that it involves carbon dioxide, a significant amount of carbon dioxide, which can cause gassing within the cells, which creates a problem. And then finally, the solvents. Most commercial lithium-ion battery solvents contain predominantly carbonates, which we'll go over again. Although esters and ethers are also two different solvents that have been investigated significantly for various reasons that we will address. So what is the electrolyte? So the electrolyte is a combination of salts, solvents, and possibly additives. Most electrolytes are composed of a single salt, which has high ionic conductivity, and typically has to have good electrochemical and also thermal stability, because as we've already said, the electrochemical potential window of the lithium-ion battery is typically in excess of 4 volts between the anode and the cathode. It's a very broad electrochemical potential window, and therefore the electrochemical stability of the electrolyte is of critical importance, as is the thermal stability of these electrolytes. Because once again, most applications for a commercial lithium-ion battery for consumer electronics devices, you're wanting the battery to last at least 4 or 5 years. And for electric vehicle applications or for grid scale storage applications, you're talking on the order of 10 years. In those kinds of applications, there may be thermal excursions by the car sitting outside, the vehicle being outside, or just the charging and discharging of the cells, which can heat up the cells and cause long-term stability issues, which is typically considered or referred to as calendar life stability. So the most of the electrolytes are composed of a mixture of solvents. It's typically a blend of solvents, and this is usually because of the fact that any individual solvent, the properties of that solvent are not ideal. Either the dielectric constant is too low, or the viscosity is too high, or something such as this. So you typically have a mixture of solvents where you get some good properties from one solvent, some good properties from another solvent, and then by blending the two solvents together, you get an advantageous mixture of the two properties, and you get the best of both worlds in terms of the solvent properties. And so then additives, most commercial lithium-ion batteries, at least as of today, have some kind of additives which are incorporated into the electrolyte formulation. And generally, the additives are incorporated to improve some kind of property of the battery. Most frequently, the additives are added to improve the stability of the anode-solid electrolyte interface. However, there are various other aspects, as we will see over the course of today's lecture, that additives are incorporated into battery formulations for. These include problems with high voltage stability, where there are high voltage additives. There may be additives which are incorporated, which make the SEI more conductive. So if you have an application where you need really good low temperature properties, or you're looking for high rate cycling, in those cases, you may want an additive that modifies the SEI so that the SEI has higher ionic conductivity. So currently, the state-of-art electrolyte for lithium-ion batteries, which has been basically the case now for over a decade, is roughly 1 molar LiPF6 or 1.2 molar LiPF6 in a mixture of ethylene carbonate and some kind of dialkyl carbonates. And usually they contain some kind of additives. VC, vinylene carbonate, which we'll go over, is the most far and away the most widely utilized electrolyte additive. However, there are various other additives that are pretty common. The vinylene carbonate is typically added as a SEI stabilizing additive. It generates a more stable, longer life solid electrolyte interface for the lithium-ion battery. So solvent. What are the solvent requirements? So first, the solvent needs to be able to dissolve the salt. and it usually needs to have a high dielectric constant, or at least one of the solvents that's blended into the electrolyte needs to have a high dielectric solvent constant. This is because a high dielectric constant is basically going to help to ionize the salt. So what you need to do is not only dissolve the lithium salt, however, you typically need to separate the lithium cation from the anion of the salt so that the cation can have greater mobility and freely move through the electrolyte solution. Solvents also need to have a low viscosity. Once again, if the viscosity of the electrolyte is too high, this basically impedes ion transport, which will impede higher rate performance, will also inhibit low temperature performance. Solvents, as I said, need to have a very wide electrochemical potential window. They need to have a high oxidation stability and low reduction stability or potential. So basically you need to have a very broad range of electrochemical stability for the solvents. And this is certainly a large problem for most of the solvents that one would consider. Of course, going back up to our high dielectric constant, basically these solvents must be polar aprotic solvents. We can't have any protic solvents such as alcohols. We need to have the absence of protons available because they would react on the surfaces of the electrodes. The other thing is solvents should remain liquid over the temperature range of the performance. So basically you want to have a very broad melting point and boiling point range for these solvents. They need to have a high boiling point. They need to have a low melting point because once again, you need the solvents to remain in the liquid phase over the entire temperature range that you would want to use the battery for. Because if it becomes a solid, then there is no or very minimal ion mobility upon the solvents solidifying. And at the same point, if you get to the boiling point of the solvent or close to the boiling point of the solvent, basically that will convert the solvent into a gas, which would then create pressure problems within the cell and cell gassing. And finally, which is really important here too, is the solvents, they need to be safe. So ideally you want them to have a high flash point, because if they have a high flash point, the likelihood of the solvents, if they somehow escape from the battery, from the cell during some event, say a car crash, car accident, where somehow the cells are punctured, you would not want to have solvents that have really low flash points that instantly catch flame with even moderate heat. Of course, you want low toxicity, once again, for the production side. To be safe for the people that are working in the production facilities. And at the same point, you want low toxicity related to the fact that when these batteries are used, or if they're damaged, or if they're thrown away into the garbage, that there is not toxicity problems with the leakage of these solvents out of the batteries and into the other materials. And then finally, which is, once again, really a critical aspect with these things, is that they need to be inexpensive. And, this is an important aspect with conducting research in the area of lithium-ion batteries. It's important to remember that inherently this is an applied science, because you're trying to develop a device that's going to store electrochemical energy and is going to be usable. And if you develop something that works really well, but the cost of it is completely prohibitive, then while you certainly may, from the basic science side, learn some very important things from this investigation, from the commercial standpoint and from the applied science standpoint, the likelihood of that invention or that discovery being useful is not very high. So the solvents that are most frequently utilized in lithium-ion batteries, as I said, are carbonate solvents and possibly some ester solvents. Ethylene carbonate, the structure shown here, is certainly a critical component of all commercial lithium-ion battery formulations, because EC is very critical in the overall formation of the solid electrolyte interface. As you can see, there's one large problem with ethylene carbonate, is that the melting point here is at 36.4 degrees centigrade, which would make this material generally a solid at room temperature, which makes a large problem associated with it. However, if you see propylene carbonate, which has a comparable dielectric constant to the ethylene carbonate, has a much lower melting point, and so this is a very good liquid. However, the problem is that if you use PC-based electrolytes, you do not generate a good solid electrolyte interface, SEI, on the anode. However, if you do use EC electrolytes, you do generate a good SEI on the anode. And so once again, basically EC is the preferable solvent over PC. But as you might imagine, since this melting point is very high, this is what is one of the things that necessitated the blend of different solvents. And so what is typically utilized are some blends of dialkyl solvents, dialkyl carbonate, such as dimethyl carbonate, diethyl carbonate, or ethyl methyl carbonate, which once again, what you can see here is now the melting points of these are very low, especially DEC and EMC. But unfortunately, the dielectric constants are not particularly high. So that's why when you blend the two solvents together, you get a mixed solvent, which has both high dielectric constant and low melting point, which is what you would need for the electrolyte formulations. So ether solvents are another one which has been thoroughly investigated for lithium-ion batteries. With this in mind, basically we have series of ether solvents such as DME, dimethoxyethane, THF, 1,3-dioxylane, this guy, which are all relatively widely used. They've got all of them very low melting points, so that's very good. They all have relatively moderate dielectric constants, acceptable but not necessarily great. But the biggest problem with the ether solvents is these are oxidatively unstable against most cathode materials for lithium-ion batteries. These are widely utilized in lithium metal primary batteries. They also are the solvent of choice for lithium air batteries or lithium oxygen batteries and lithium sulfur batteries, which are lower, well, the potential as cathodes variable there, but nonetheless, that's where the research is being developed with these solvents. Commercialization, we'll see lithium sulfur is somewhat close to commercialization. However, lithium oxygen is quite far and I would say quite unlikely to see commercialization anytime soon. Nonetheless, these ethereal solvents are good solvents for the lithium primary systems. So ethylene carbonate versus propylene carbonate, as I just mentioned, EC's got a very high dielectric constant. PC's got a pretty high dielectric constant too, similar, but unfortunately the melting point here is 36 degrees centigrade, quite warm, and the low melting point of the propylene carbonate is quite low. But the biggest advantage of EC is it allows the formation of a stable anode SEI, while PC does not form a stable SEI, which then leads to the continuous exfoliation of graphite and the continuous reduction of the electrolyte upon cycling. Unfortunately, this difference is poorly understood, but some of the research that we've done in my research group over the last decade, and also some research that's been done in Professor Abe's laboratory, really has provided some insight into what this difference is, and we will go over that in the next lecture. So basically, going on to this, the original observation of ethylene carbonate versus better performance versus propylene carbonate was observed by Professor Jeff Don, who's one of the leaders in lithium-ion battery research and also leaders in electrolyte. And basically what they observed was that they observed that the ethylene carbonate generated a stable passivating film on the surface of the graphite anode, while the propylene carbonate did not, and led to continuous exfoliation of the graphite and continuous reduction of the solvent. So the linear carbonates, dimethyl and diethyl and ethyl methyl carbonates, as what I already mentioned, these linear carbonates have lower boiling points, lower viscosity, and also lower dielectric constant. One really nice advantage is that they form homogeneous mixtures with EC in any ratio. So basically you can mix any ratio, 1 to 10, 10 to 1, and anywhere in between of EC and these dialkyl carbonates, and it becomes homogeneous. And the solvent mixture has a synergistic effect, allowing both the high electrochemical stability, good ionic solvation, and low viscosity. And so these electrolyte formulations, these blended electrolyte formulations have very good high ionic conductivity also. So the EC-DMC mixtures, dimethyl carbonate, were the first most widely investigated electrolyte formulations. However, these didn't have as good low temperature performance. They were fine for room temperature, However, as more interest in low temperature performance came up, two different electrolyte formulations took over, which are the EC, DMC, DEC in roughly a 1:1:1 blend, or the EC, EMC, ethyl methyl carbonate in a 3:7 blend. And this was primarily due to the preference for low temperature performance. And I would say at this point in the lithium-ion battery community and commercial cells, the EC, EMC formulation, somewhere in this 3:7 region, is the more frequently utilized formulation, but certainly dimethyl and diethyl carbonate are still widely used. So this development of the EC-DMC electrolyte was originally conducted by Professor Tarascon with Professor Guillemard. And basically what they observed was that very nice performance of the cells. Once again, this is an example of cycling performance, capacity as a function of cycle number. And they showed the charge and discharge curves as the 50th cycle versus the 200th versus the 400th. And for this novel electrolyte formulation, what you can see is the charge and discharge curves do not change dramatically. So we charge the cell, then we discharge the cell. You lose a small amount of capacity, which once again is observed here. The capacity is lower after 400 cycles than it was after 200 cycles, or if it was after 100 cycles, which is basically where this point is along the curve. So the further advances of the electrolyte formulations to improve low temperature performance were largely conducted at the Jet Propulsion Laboratory and associated with Caltech in Pasadena by Marshall Smart and Kumar. And basically what they observed was that if they instead of using the EC-DMC blend, they used the EC plus diethyl carbonate, or even better, EC plus DEC and DMC in the 1:1 blend. What they saw is this is just a simple discharge curve at -20 degrees. And what they see is with the EC-DMC electrolyte, they get a pretty small percentage of the overall capacity. However, with the EC-DEC-DMC blend, they get a much higher capacity upon the discharge, which is also shown here, which I apologize for the poor quality of the image. But nonetheless, at room temperature at 23 degrees centigrade, you can see all three of these electrolytes have a fairly similar discharge capacity. However, as we go to lower temperature to 0 degrees and then down to -20 degrees, you can see that EC-DMC has a very poor discharge capacity, which is also displayed here, while the EC-DEC-DMC electrolyte has a very high discharge capacity, as shown also here. And once again, this is due to the fact that by lowering the temperature, this electrolyte formulation stays a liquid and the viscosity does not increase significantly, while the viscosity of this electrolyte has probably increased significantly, resulting in increased resistance or impedance of the cells upon trying to cycle it at low temperature. So another example with work that was done at the Jet Propulsion Laboratory was that for a lot of their applications, which were extreme low temperature applications, these were applications for batteries in space, where they needed to have a good discharge capacity at -40 degrees centigrade. In addition to their baseline electrolyte was this, which was now this EC-EMC, the 3:7 blend, 3070. They also looked at methylpropionate, basically an ester, and incorporating various concentrations of the ester into the electrolyte formulation. And what they were able to observe was they got much better discharge performance at various rates, which is what these plots are showing. This is going from a slow discharge to faster discharges. And once again, same thing here. And what they show is they can still retain most of the discharge capacity at -40 degrees at even the higher rate discharges. Which once again goes to the fact that by incorporating the methylpropionate into the electrolyte formulation, you've improved this low temperature performance. Now, generally within lithium-ion battery electrolytes, there's always a trade-off. So if you improve one aspect of the performance of the electrolyte, there's usually a drawback and it causes problems somewhere else. And in the case of the methylpropionate-based electrolytes, these typically lead to poorer calendar life and cycle life. And so you usually take a hit on the cycle life versus what you do to get the low temperature performance. However, current research in this area, Professor Don again has gone back and done a lot of research looking at these ester-based formulations, and these ester-based formulations in combination with various anode SEI forming additives can be used together to get both low temperature performance improvements and also the good calendar life. So other solvents that people have looked at for the lithium-ion batteries includes nitriles, such as acetonitrile and various other nitriles. The problems with these, they have potential reduction problems on the anode. They have been investigated with lithium titanate anodes, which is a slightly higher potential anode than graphite or lithium metal. So there is some interest there, but these have challenges. Also, in general, anytime that these could be degraded to generate HCN, which is poisonous, is a concern in terms of the battery industry. Sulfones have also been pretty thoroughly investigated, ethyl methyl sulfone and sulfolane. These have potentially good high voltage, they're potentially good high voltage electrolytes. However, they got really high viscosity and they've got electrode wetting problems, which basically what a wetting problem with an electrolyte is when you build a cell, you first build the cell evacuated. So you have layer after layer after layer of your electrodes, cathode, anode, or I should say cathode separator, anode, cathode separated anode, and so forth. And when you have these layerings, you build the cell together, as I showed in the first lecture, and you can wind the cell or you can build a coin cell. But then after you do this, you have to incorporate the electrolyte. And most commercial cells are made evacuated, and then you backfill with the electrolyte. But when you have a really high viscosity of electrolyte, the electrolyte can't fill into the cell very well. And also it doesn't actually wet the electrode. So when it doesn't go into and get absorbed into the electrode, similar to what water would absorb into a towel, where if you have a big puddle of water and you set the towel there, the water is wicked into the towel. Some of these solvents don't wet very well, and so they don't wick very well. So fluorinated carbonates and esters have also been fairly thoroughly investigated. Once again, these have poor wetting properties. They also have weaker ion solvation because the electron withdrawing fluoride substituents remove electron density from the oxygens of the carbonates or the esters, which makes them poor or donating solvents. They also have been reported to disrupt the formation of the solid electrolyte interface. And then finally, they're quite expensive. So a lot of these electrolyte solvents are very expensive, which once again, in terms of commercialization, is a large problem. As I said, ethers have their problems with their stability above 4 volts. They get oxidized relatively easily, which they can generate peroxides, which are explosive hazards. They're common solvents, as I said, for lithium primary and also lithium sulfur and lithium oxygen batteries. But for lithium ion batteries with lithiated metal oxides for cathodes, they're generally not utilized. Another solvent example are the ionic liquids. Ionic liquids have received a lot of attention over the last decade or decade and a half, we'll say. There's been a large amount of research into the use of ionic liquids in lithium-ion batteries. They have several problems, though. First off, they're very expensive. They also have significant electrode wetting problems. While they do have very good thermal stability, they have very poor low temperature performance, and for the most part, most researchers in lithium-ion batteries do not consider the use of ionic liquids as a near-term solution to our electrolyte problems. So some other aspects of solvents that have been utilized are non-flammable solvents. These are some examples of research conducted by Kang Zhu and collaborators at the Army Research Lab in the United States. And basically, they look at a whole series of different phosphorus-containing derivatives, trimethylphosphorus, triethylphosphorus, and trifluoroethylphosphorus. And basically, what they looked at was the different types of flammability. And what you can see is in order to get where the sample is not particularly flame retardant, which they have this flame retardant percentage, which this is a self-extinguishing test here. So basically in these experiments, they'll take a cotton ball and then put the solvent in the cotton ball, and then they'll light the cotton ball on fire, and they'll see how long it takes for that cotton ball to self-extinguish. And the quicker that it self-extinguishes, then the less flammable the solvent is. But what you can see is you have to have pretty high concentrations of the flame retardant solvent in the standard electrolyte formulations in this 1 molar LiPF6 EC-EMC to become non-flammable or flame retardant. And what this causes the problems because basically, for the most part, most of these flame retardant solvents disrupt the SEI formation, and so they disrupt the calendar life and the cycle life of the overall batteries. One of the better, most promising fluorinated or phosphorus-containing solvents, both, was the TFP solvent shown in the previous slide. And what you can see is they got pretty good cycle number with these solvents with fairly high concentrations, percentages of the the tris trifluorophosphate derivative. However, nonetheless, commercialization of these solvents has been hindered both by a combination of stable SEI formation and long-term cyclability, and then also cost of the electrolyte additive. If you're going to have to add a non-flammable co-solvent in 20 or 15 or 30% or something, it's going to need to be very, very inexpensive in order to afford the commercial viability. So the salt. What are the salt's requirements for lithium-ion batteries? I mean, first, it must be able to dissolve and completely dissociate with high mobility. And so you need to have anions that are very stable, that delocalize the negative charge of the anion very well, so that the anion is not strongly associated with the cation. So you need to have salts where you can dissociate the ions well. The electrochemical stability to reduction on the anode or oxidation on the cathode is also very critical. So we need to have a wide electrochemical stability window for both the salt and the solvent. The anion should be inert to solvent and thermally stable. So once again, in order to have a long calendar life, these salts need to be something that doesn't decompose easily, and it also can't react with the solvent that you're dissolving it in. The anion also must be stable to the separator, the current collectors, and also the packaging material. So if we're using a stainless steel can to make the cell, or if we're using some aluminum flexible packaging material, which may be used in pouch cells, the anion can't corrode or damage those materials, which is a problem for some salts. The salt should also be non-toxic, and it also should be inexpensive, because once again, it can't be extremely expensive or else this is going to be a problem, nor can it be toxic. Another important thing is that the anion needs to be low molecular weight, because if you have a really large molecular weight anion, the anion is not really doing much. Ideally, it should just be allowing the lithium ions to go back and forth. If you have something that is high molecular weight, you're adding a lot of mass to the cell, which is going to decrease your gravimetric energy density. That's really effectively not doing anything for you in terms of the production of the cell. So what are the salts that are utilized in these lithium batteries? So as I mentioned at the beginning, lithium tetrafluoroborate, LiBF4, is a very good salt. LiPF6 is the most widely utilized salt. Lithium arsenic hexafluoroarsenate is another one, which was one of the first salts utilized for lithium-ion batteries. And lithium perchlorate is also another one that's received a lot of attention. These all have pretty high conductivities in your blend of EC-DMC, pretty reasonably high conductivities, as do the lithium triflate, or I should say the lithium imide, which in this case is lithium bis trifluorosulfonylamide. This is LiTFSI, which is not very nice high conductivity. And then, of course, there's also, since this paper was published, this is actually the 2004 version, not the 2014 version, of the Chem Review article by Kang Zhu. There's a lithium LiFSI, which is another very interesting salt with comparable conductivity to the lithium TFSI, this guy here. And then another salt that's received a significant amount of interest is lithium difluorooxalato-borate. And so we'll kind of go over each of these salts here quickly. So first off, lithium perchlorate. Lithium perchlorate has very good solubility, has good conductivity, and reasonably decent oxidative stability. However, lithium perchlorate itself is a strong oxidant which can react explosively with organic solvents. And so while there's a lot of use of lithium perchlorate in research lithium-ion batteries, so if you're trying to understand the effects of different salts, LiPF6 versus something else, lithium perchlorate is a good example, but commercially it cannot be used. Lithium hexafluoroarsenate, once again, this was the first salt used in commercial lithium-ion batteries. It has very good solubility, very good conductivity, and very good oxidative stability. So many of these are very, very good properties. It has reduction reactions which occur at about 1.15 volts, which is not dramatically different than lithium hexafluorophosphate, but the lithium hexafluoroarsenate is highly toxic, also relatively expensive, and once again is really no longer considered a salt of interest in the lithium-ion battery field. Lithium tetrafluoroborate. Now this is a salt that really has, still some potential interesting effects. It's got some good solubility. It's also got very good oxidative stability. Moderate conductivity. It's a little bit lower conductivity than what you see. So we can go back one slide here. A little bit lower conductivity than what you see for LiPF6. Not necessarily prohibitive, but in addition to this, the LiBF4 typically makes a more resistive interface than does LiPF6. So you have two aspects there that are negative with the LiBF4, is that it both has slightly lower conductivity, but it also generates a more resistive interfacial film, SEI, on the anode, which prohibits use in most applications. It does have better high temperature stability than LiPF6. It's a very potentially interesting salt. And especially right now, there's also been a lot of studies done for high voltage applications where LiBF4 shows significant promise for use as a salt for high voltage cathodes. So as I said, LiFSI and LiTFSI, these are two of the more recently developed salts. They've got really good conductivity, very good thermostability, and good electrochemical stability. The biggest problem with both of these two salts is that they cause corrosion of the aluminum current collectors. And so as I mentioned in the presentation, the first presentation, the current collector on the cathode side is aluminum metal. If you use either TFSI or LiTFSI, these corrode the current collector, damaging the current collector and effectively damaging the cell. So this is a significant problem. There are some ways to avoid this problem, but in most electrolyte formulations that are primarily composed of LiFSI or LiTFSI, this continues to be a limiting factor. Another problem with these is they're quite expensive, much more expensive than LiPF6. Now, the LiPF6 itself was a very expensive salt earlier on in its investigation. However, as the salt was scaled up, the cost came down, and so it's not inherently necessarily a problem with these materials, but at the moment, it is a concern. As I said, lithium bisoxalato-borate, LiBob, moderate stability, moderate conductivity, pretty good thermal stability. It's had some purity complications, and one of the biggest problems with this is upon reduction on the anode side and also oxidation on the cathode side, the oxalate species are converted into CO2 gas, which causes cell gassing, which can cause cells to swell and hurts the overall performance. A better salt than LiBob is lithium difluorooxalato-borate. Half-Bob is what's frequently referred to as. This one has very good solubility, much better solubility than LiBob, moderate conductivity, very good thermal stability. I would say it's once again a potentially interesting salt. It's got some problems. Once again, it also generates CO2 from the oxalato ligand, but I think it has as much promise as the LiFSI and TFSI. That brings us to the salt that is the most widely utilized commercial salt, LiPF6. LiPF6 is not ideal but it has the best combination of properties. It's good solubility, good conductivity, good ion mobility, good electrochemical stability, and stable SEI. It's really the only commercial salt used in lithium-ion cells. The biggest problem with it, which we'll see in just a second, is it's got moderate thermal stability and hydrolytic stability. And basically the use of EC and LiPF6 in lithium-ion batteries, which is what is the electrolyte formulation with the dialkyl carbonates. The biggest problem is it limits the temperature range from about -20 to +50 degrees C, and also limits the calendar life. But as we'll see, by combining these salts and solvents with electrolyte additives, we can expand this range and expand the calendar life, or extend the calendar life. So going back to the thermal stability issues of LiPF6, it has been reported by John Kerr and coworkers that LiPF6 thermally decomposes to generate PF5 and lithium fluoride. So if you just heat up the salt. And it's also been reported that if you take PF5 and expose it to water, you can generate phosphorus oxyfluoride along with HF. Both PF5 and phosphorus oxyfluoride and HF are all strong Lewis acidic species. And these species can react with something like ethylene carbonate with a related Lewis acid, 10-tetrachloride, and to polymerize the ethylene carbonate. So once again, the generation of these acidic species from the decomposition, from the thermal instability of LiPF6 can then result in other subsequent problems with the electrolyte formulation. So some research done in my lab a little over a decade ago, 15 years ago, basically we monitored just the electrolyte formulation. So we took LiPF6, dissolved it in diethyl carbonate, and heated the sample for 100 degrees centigrade for 63 hours. And basically what happens is the electrolyte starts to decompose. As the electrolyte decomposes, we monitor this by fluorine and phosphorus NMR spectroscopy. We start off and we have lithium hexafluorophosphate characterized by a doublet and a septet for the lithium and for the fluorine and the phosphorus. However, we start to observe new species characteristic of doublets and triplets in the phosphorus and fluorine NMR, which are characteristic of these species here, which is difluoroethyl phosphate and fluorodiethyl phosphate, along with ethyl fluoride. And basically what's happening is the LiPF6, which is then decomposing into PF5, reacts with these carbonate solvents to generate these mixture of components. We can also characterize the thermal decomposition of this ternary mixture, the EC, DEC, DMC mixture of the electrolyte formulation, and we see a whole range of different fluorophosphate species. We see ethers, alkyl fluorides, and along with CO2 gas as these materials thermally decompose. So we as a summary of the overall decomposition products from the LiPF6 and DEC, DMC, EMC, and EC, basically we see a whole range of ethers that are generated along with oligoethylene oxide. So we do see polymerization reactions. We see fluorophosphate species, which are generally all strong Lewis acids, also fairly toxic species. We see alkyl fluorides, and we see carbon dioxide. And what was also interesting with this is in terms of the commercialization of lithium-ion battery electrolytes, if we add low concentrations of alcohols to the electrolyte formulations or low concentrations of water, it was easier to add the alcohols, what we see is we see an exponential rise in the decomposition or the generation of the difluoroethyl phosphate species, as monitored by fluorine NMR, which is consistent with an autocatalytic decomposition mechanism, where basically if we have even trace impurities of water or alcohol, which is basically impossible to completely remove all of the water and residual alcohols from carbonate solvents, that when we heat the sample up, the LiPF6 dissociates into lithium fluoride and PF5. The PF5 rapidly reacts with these trace alcohol impurities to generate phosphorus oxyfluoride, which initiates the autocatalytic decomposition by reacting with another equivalent of carbonate solvent to evolve CO2 to generate a new phosphorus oxygen bond, which then can react with another equivalent of PF5 to then turn the autocatalytic cycle around to generate a new fluorophosphate species and then regenerate the original fluorophosphate species or trifluorophosphate, which once again, this ultimately, since we're doubling the amount each time the cycle turns over, this results in an autocatalytic decomposition of the electrolyte. So the next section is electrode interfaces. And so, as I've already mentioned, the solid electrolyte interface on the anode of lithium-ion batteries is a critical component, which is generated during the first charging cycle of the lithium-ion battery. This solid electrolyte interface was originally proposed by Professor Pellet back in 1979, and he showed it, depicted it as this kind of mosaic representation of a number of different insoluble lithium species, including lithium oxide, lithium fluoride, lithium carbonate, polyolefins, and semicarbonates. And so the importance of this solid electrolyte interface on both graphite anodes and then also lithium metal anodes has been something that's received an intense investigation since Professor Pellet originally proposed this back in 1979. So if we compare the overall lithium intercalation of graphite into graphite with and without an SEI film, what you can see is if you don't have the solid electrolyte film, in addition to the lithium ions intercalating into the graphite, you also see solvent molecules intercalating into the graphite, which basically disrupts the overall structure of the graphite, causing the graphite to exfoliate, and at the same time causing the solvents to continuously reduce to generate more solvent decomposition products. However, if you do have a protective solid electrolyte interface on the surface of the graphite anode, basically the lithium ions are able to be transported through this solid electrolyte interface, because the solid electrolyte interface by nature is lithium, must be lithium ion conducting. However, it inhibits the solvents from approaching the surface of the graphite electrode. And since the SEI must also be inherently electrically non-conductive or electrically passivating, it inhibits the overall reduction of the ethylene carbonate molecules. So the SEI formation mechanisms, or I should say these are more so proposed possible routes, were originally proposed by Doron Arbach and co-workers back in 1996. And basically, under these studies, they didn't conduct a mechanistic investigation of how the SEI's products were formed. What they did, though, observe was a whole bunch of different products. And then upon observing the products that they saw on the surface, which is what the SEI was composed of, they went back and they proposed a whole bunch of plausible routes that these species could be electrochemically reduced to generate the species that were observed on the anode SEI. However, as subsequent research has gone forward, the observation has been that not only can electrochemical reduction reactions occur on the surface of these electrode materials, but there also may be related thermal reactions of the SEI components that cause the SEI components to evolve. And that's something that we'll discuss in significantly greater detail as a result of some of the research conducted in my laboratory in the next lecture. So another aspect of the solid electrolyte interface on the anode, which is really critical, is that basically the solid electrolyte interface changes over time. And so back in the early 2000s, a series of papers were published from Argonne National Laboratory, many of them in collaboration with the University of Uppsala, in which researchers did a detailed investigation of how the solid electrolyte interface changes for US Department of Energy program cells over time, over cycling life. And so what they wanted to see was how these lithium ion cells changed as you started to observe power fade, or as you started to observe capacity fade. And what was observed is that basically you started off and you have your fresh graphite particles. The edges of these graphite particles look pretty clean. You can see that they've got some kind of surface film on them. This is on the fresh 0% power fade. However, the cells after 50% power fade, you can clearly see that the surface film is much, much thicker and on the surface of the graphite particles. And in addition, if you go back and you look at the, so this is an SEM image, if you look at X-ray photoelectron spectroscopy, XPS, which can give you elemental characterization of the surface of the electrodes, what you can see is the sample with 0% power fade has relatively low concentrations of fluorine and relatively high concentrations of carbon. However, after 35% power fade, what you see is much higher concentrations of fluorine, which lasts pretty thick. This is at sputtering time. This is effectively a depth profiling, and also much lower concentrations of the carbon-containing species. So what this shows you is that the SEI is changing over time. So it starts off with one composition, and as you continue cycling and aging the battery until the point where you've lost 35% of the overall power that was originally in the battery, then you have a case where the SEI is changed. And so once again, what we'll see in the lecture tomorrow, or the next presentation, is a detailed mechanistic investigation of how this evolution of the SEI occurs, and then also how you might be able to stop it. So another investigation by Professor Li at the National Taiwan University, what they were able to observe was that in LiPF6 versus lithium perchlorate, you see an evolution of the SEI, where you see SEI degrading and reforming and degrading and reforming in the case of LiPF6, which you don't really see with lithium perchlorate. And they attribute this largely to the presence of PF5 and the Lewis acidity of the PF5, which results in a corrosion and a damaging of the anode SEI. And this can be observed by looking at electrochemical impedance spectroscopy, which once again, this is a measure of the overall impedance of the cell. And if you remember, smaller semicircles are good and larger semicircles are bad. And what they observe with this is at 25 degrees centigrade, over your storage from 1 to 2 to 3 to 7 days, there's really not a significant change in the overall impedance of the anode SEI. However, if they do the same storage at 80 degrees centigrade, what they see is large, small, large. We see a large alternating effect of the overall SEI impedance. And what this suggests is that the SEI is degrading and then reforming and degrading and reforming and changing under these conditions. So as summary of this solid electrolyte interface, the SEI results from the reduction of the electrolyte. It must allow lithium ions to intercalate and deintercalate into the graphite anode. However, it also must be electrically insulating. In general, one of the problems with it is it's not particularly thermally stable. The formation mechanisms are not fully understood, but we'll go into greater detail in the next lecture regarding this. And what we've been spending a lot of time doing is understanding the role of the salt, the solvent, and the additive in SEI formation, and then also evolution. As I said previously, there's a lot of anode SEI film forming additives that have been utilized, including vinylene carbonate and LiBob, and we'll go over some of those. The same point from the summary that I just mentioned from the paper by Daniel Abraham and coworkers is you start off with an SEI which is generally considered to have solvent reduction products and then kind of an organic layer. However, over time, this evolves and changes and becomes much more inorganic in nature, and trying to understand why this evolution occurs from the SEI that's initially formed to the SEI that's present after a long-term cycling or calendar life aging is something that's a critical component of improving the overall long-term performance of lithium-ion batteries. So what about the cathode side? So as I mentioned, the solid electrolyte interface on the anode is a very important aspect in terms of the stability, because the electrolyte is not stable to the reduction potential of lithiated graphite. However, there are also interfacial films that are generated on the cathode side. And in the same series of paper from Argonne National Laboratory, what they observed was that the electrolyte, LiPF6 electrolyte, decomposes on the surface of the lithium nickel cobalt oxide based cathodes to generate lithium fluoride and lithium fluorophosphate based species on the surface, along with oligocarbonates or lithium alkyl carbonates and lithium carbonate. And basically what you see is a lot of electrolyte decomposition products on the surface of the cathode upon aging of these cells. So this is once again after the long-term cycling and calendar life performance. What we observed at the time is you can observe very, very similar surface films on the cathode from just thermal reactions. And so if you take lithium cobalt oxide or lithium nickel cobalt oxide, you store these in just the electrolyte. This is no additional cycling. There's no cycling at all. This is just cathode particles stored in the electrolyte. And what we observe are very similar cathode surface films to those that were reported on the surface of these U.S. Department of Energy program cells. And so what this suggests is on the cathode side, while there may be some oxidation reactions of the electrolyte on the surface of the cathode, and certainly if you start charging the cells to high potential above 4.1 volts versus lithium metal, there are more oxidation reactions. However, some component of the reactions that were observed on the DOE program cells is related to just the thermal decomposition of the electrolyte and the reaction of these thermal decomposition products with the surface of the cathode. So we also observed that cathode films can be formed at very high potential. So looking at the high voltage spinel, the lithium nickel manganese oxide, and if we take the electrolyte formulations and build cells, but instead of cycling cells, we store the cells at various potential, what one can observe is if the potentials of the cells are relatively low, 4.0 or 4.3 volts, we don't see very much residual current flow through the cell. However, if we go to very high potentials, 4.7 or 5.0 or 5.3 volts, we see a large amount of residual current flow. Now, this is utilizing cathode materials which have already been delithiated. And so basically this residual current flow is simply only from side reactions, from decomposition reactions. And then if we look with IR spectroscopy, we can see that the cells that were stored at low voltage, basically there's very little electrolyte decomposition on the surface, consistent with very low residual current flow. However, for the cells that are stored at high potentials, we see a significant change in the IR spectrum of the surface of the cathode, and which is consistent with the high residual current flow. And what we observe predominantly is the generation of polyethylene carbonate. So we have oxidation reactions of the electrolyte, which can generate polyethylene carbonate, and we also have thermal reactions of the electrolyte, which can generate fluorophosphates and ethers on the surface of the cathode materials. And so trying to deconvolute these separate reactions, both the oxidation reactions and the thermal decomposition reactions, is something that we'll be spending a significant amount of time with in the fourth lecture of this series. So electrolyte additives. So a lot of electrolyte additives have been investigated in commercial lithium-ion batteries. And the purpose of these additives varies for different types of electrolytes. So first and foremost, the most widely utilized additives are SEI film forming additives. These include vinylene carbonate, which is pretty much in most commercial lithium-ion batteries, also fluoroethylene carbonate, and lithium bisoxylato-borate. All three of these additives can be used to generate a more stable or a better anode solid electrolyte interface. And there's various advantages and disadvantages of these different electrolyte additives. There's also thermal stabilizing additives. So as I mentioned earlier, LiPF6 is inherently a thermally unstable salt, which can dissociate to generate PF5. Which is a strong Lewis acid. If you add various Lewis basic species, including dimethylacetamide or phosphates or phosphites, these additives can inhibit these thermal decomposition reactions by acting as Lewis bases to bind the Lewis acidic species. We also have cathode film forming additives such as nitriles or fluorinated carbonates. These additives have been reported to passivate the surface of the cathode, especially at high voltage, and inhibit the further electrolyte oxidation at the surface. However, unlike in the case of the SEI forming additives, where these additives are very clearly deposited on the surface of the anode to generate a more stable anode SEI, the mechanism of function of many of these cathode film forming additives or cathode stabilizing additives is really not particularly clear. The surface interfaces that are present on the cathode are still quite poorly understood, we'll say, and the surface reactivity of the cathode is still poorly understood. There's also overcharge protection additives, which are redox shuttles, which basically can prevent the cell from going into overcharge. There are also flame retarding additives, which we already mentioned this earlier, which are predominantly phosphorus containing co-solvents or also heavily fluorinated co-solvents. These can be used to inhibit the flammability of solvents and inherently make more safer lithium-ion batteries. So some of the examples of these SEI enhancing additives are shown here. Many of the SEI containing additives contain some form of unsaturation, some kind of a carbon-carbon double bond. And the reason that these carbon-carbon double bonds are incorporated is that usually it's perceived that you have some polymerization reaction, and this polymerization reaction results in the generation of a polymer on the surface of the anode, and this polymer improves the SEI stability. Vinylene carbonate, VC here, is, as I've said, the most widely utilized electrolyte additive. Most commercial lithium-ion batteries contain some VC, typically about 1%, maybe 1.5%. However, fluoroethylene carbonate here, FEC, is another electrolyte additive that's received a lot of attention, especially for silicon anodes or graphite silicon composite anodes, because the FEC has been reported to generate a better SEI on these silicon surfaces. But there's been several other investigated species. Many compounds have been synthesized, and many compounds have been tested as electrolyte additives. And some of them have good performance and not so good performance, but once again, VC is still probably the top species. Some other examples of additives, which are, there are some other heteroatom containing species, which contain nitrogen, or also boron containing species. We're going back to LiBob. LiBob can generate these strong surface films on the anode along with half-bob due to the reduction of these species on the surface. So an example of the vinylene carbonate, which was originally patented by Saft before 1997, the patent was published in 1997. Numerous investigations, many investigations of vinylene carbonate have been conducted to try and understand what vinylene carbonate does in cells. This is one example of this. And what was observed was that as you vary the concentration of VC from VC-free electrolyte formulations to low concentrations of VC to pure VC electrolyte, it's quite clear, once again, from X-ray photoelectron spectroscopy on both the surface of the graphite and on the surface of the lithium cobalt oxide, is that the vinylene carbonate is clearly being oxidized to generate some type of polymer, poly-VC, on the surface of both the cathode and the anode, and that these surface films somehow stabilize the lithium-ion battery for longer-term calendar life cycling, which we will go over in greater detail in the next lecture. Similar investigations were conducted with LiBob. LiBob was investigated as an additive, not only as an alternative salt, but LiBob was investigated as an alternative additive, and that's because it generates a more stable anode SEI. The LiBob is reduced on the surface of the anode, and what we observe is this, species of oxalato species. We see significantly deposition of the oxalato species as we drop the potential of the cell. We also observe high concentrations of boron on the surface of the cell that contains LiBob electrolyte. And what was proposed was that the LiBob salt itself decomposes on the surface to generate this oligomeric or polymeric borate species on the surface, and that this polymeric borate species on the surface, which may have similar structural properties to polyvinylene carbonate, is what imparts the overall stability of of incorporating LiBob onto the surface. Other investigation which was conducted in our research group was on the design of thermal stabilizing additives. As I mentioned, PF5 and phosphorus oxyfluoride are very strong Lewis acids and can decompose the carbonate solvents. If we can design additives that inhibit this acid-base interaction between the Lewis basic carbonates and the Lewis acidic PF5 and phosphorus oxyfluoride, we can inhibit the reaction. We add really good Lewis bases such as triethylamine. We end up having a white precipitate form, which is the PF5 triethylamine complex. However, with pyridine or HMPA or dimethylacetamide, these provide very good thermally stable electrolytes. However, the additive must also be electrochemically stable. And of these solvents that are investigated, dimethylacetamide is really the most promising electrolyte additive, and this is an electrolyte additive that has been incorporated into commercial cells. So examples of this is if we take LiPF6 with our standard electrolyte formulation here, this is LiPF6 in 1:1:1 EC-DMC, and we store the sample at 85 degrees centigrade for 160 hours. Basically, the electrolyte degrades. It turns black. You start to see precipitation, complete thermal decomposition. There's also a lot of pressure built up in this tube. However, if you add just a low concentration of the thermal stabilizing additive, HMPA or dimethylacetamide, this is thermally stable for 1,600 hours at 85 degrees centigrade. No evidence for thermal decomposition whatsoever. We can observe that the reason we're observing this increased thermal stability is that we generate a HMPA, hexamethylphosphoramide complex with PF5, which is observed by both phosphorus and fluorine NMR spectroscopy. And the presence of this HMPA PF5 complex inhibits the reaction of the PF5 with the Lewis basic carbonate solvents. And so it inhibits this decomposition reaction and therefore stabilizes the electrolyte. And now if we compare the capacity retention of some cells after thermal abuse, thermal storage, with different electrolyte additives, the standard electrolyte formulation versus LiBob versus vinylene carbonate versus dimethylacetamide, we can say in this particular case, the incorporation of the dimethylacetamide gave us our best capacity retention after a 30-day storage at 70 degrees centigrade. 30 days storage at 70 degrees centigrade are pretty strongly abusive conditions, and this certainly was very promising that we retained the majority of our capacity after this 30-day storage. Other electrolyte additives of interest include overcharge protection. These are typically redox shuttle species, which the additives are reversibly oxidized at potentials slightly higher than the potential of the cathode. Then they diffuse over to the anode, where they are then subsequently reduced, and they basically go back and forth between the cathode and anode, and this can inhibit the overcharge of the cells. Another type of electrolyte additive related to this are called shutdown additives. These are additives which are irreversibly oxidized on the surface of the cathode to generate a fairly thick polymeric coating, inhibit furthering overcharge. Now, in the top case, the redox shuttles, the battery can continue functioning as normal with the redox shuttle. However, these shutdown additives would destroy the battery. The battery would be dead. You'd no longer be able to charge and discharge the battery, and the battery would have to be discarded after that time. Some of these redox shuttles were investigated by Professor Don and coworkers, and what you can see is that they show, at these high potentials, you see very, very regular shuttling action, where you basically stabilize the redox shuttle, and these can last for very, very many cycles. These are basically thousands of cycles. They were able, or 300 cycles. They were able to observe 100% overcharge per cycle and no degradation of the overall cell. Another important aspect with electrolyte additives is the combination of additives. So additives are frequently, very frequently in commercial cells, most of the time investigated as combinations of two additives. So usually you have additives which are incorporated to address multiple problems within the cell. For example, you will incorporate vinylene carbonate as an SEI stabilizing additive, and then you may also incorporate a nitrile, such as succinonitrile, which can function as a cathode stabilizing additive. And many different electrolyte formulations will combine one or two or three electrolyte additives for different advantageous properties. Or another example is you can add vinylene carbonate, which generates a more stable anode SEI, with propane sultone, PS, which is frequently used as a SEI conductive and enhancing additive, or in inhibiting the generation of higher resistance. So, and many of these commercial electrolyte additives electrolytes contain a mixture of these additives. So here's an example of the investigation of electrolytes which contain standard electrolyte formulation with 2% vinylene carbonate, or 2% propane sultone, or 2% propane sultone plus vinylene carbonate. And once again, what you can see is the cells with the VC and the propane sultone have both better capacity retention at 55 degrees centigrade, and also higher coulombic efficiency, which is the charge over discharge versus compared to the discharge is the efficiency. Ideally, you want a 100% efficiency, so your charge and discharge capacities are the same. However, frequently you get less than that because basically some of your charging capacity goes into the electrochemical decomposition of the electrolyte. But also with this combination of VC and propane sultone, it improves the high temperature stability and also lowers cell impedance. So in related investigations, the electrochemical impedance is reduced by this combination of propane sultone and vinylene carbonate. And so once again, by utilizing a mixture of additives, you can get beneficial properties from the combination. So as I said, other electrolyte formulations outside of additives have been investigated a lot over the last few years. Here at the end of the presentation, we're just kind of briefly going to go over some of the advantages and disadvantages of these different electrolytes. So as I have already mentioned, ionic liquids. There's been significant interest in these ionic liquids over the last 10 to 15 years. Due to a combination of really good thermal stability and also high conductivity. The biggest problems with these ionic liquids is that there's very, very high cost, and they're also relatively difficult to purify. And one of the big problems with lithium-ion batteries is lithium-ion batteries are frequently extremely sensitive to low levels of impurities. And so if you have difficulties generating very, very high purity components, such as the electrolyte, that can really cause you problems. As I said earlier, the ionic liquids also have significant problems with the low temperature performance and also electrode wetting. They don't really absorb into the electrodes very well. They kind of stay on top of the electrode, and you need to have good contact between the electrolyte and the electrode, the entire surface of the electrode, in order for you to get good transfer of the lithium ions from the electrolyte into the cathode material or the anode material. The properties of these can be improved by combining them with standard solvents, standard carbonate solvents and LiPF6. The biggest problem with that, however, is that frequently what happens is you kind of get the worst of both properties. You still don't have very good wettability because you have LiPF6. Now your thermal stability is not that good. And so typically when you combine the carbonate solvents with the ionic liquids, what you get is an overall electrolyte formulation, which doesn't give you the best of the both worlds. You get kind of the worst of both sides. And this is just not a near-term solution to the problem for lithium-ion battery electrolytes. Polymer electrolytes, this is another area that there's been a significant amount of research into. These have excellent processability and very good flexibility. In general, the polymer electrolytes have much lower flammability than do the liquid electrolytes, which is one of the reasons that there's a lot of interest in polymer electrolytes. There's also the potential for utilizing the electrolyte separator as a dual function. So instead of having to also incorporate a separator, if you use a polymer electrolyte, the polymer electrolyte can be both the electrolyte and the separator. So this might have some cost advantages and also some simplification advantages in terms of cell construction. However, most of the current polymer electrolytes are actually what you would call gel polymer electrolytes, where in this case you take a liquid electrolyte and you incorporate it into some polymer matrix. But in these conditions, the liquid electrolyte is still the primary source of lithium-ion conductivity, and at the same point, the liquid is still there. And so the problems associated with flammability of the liquid electrolyte and the liquid electrolyte leaking are still present when you have these gel polymer electrolytes. They don't go away. And in terms of the pure polymer electrolytes, which are typically polyethylene oxide, the conductivities of these materials are still not very high. And once again, the wettability of the electrodes is relatively poor. And so I would say in terms of just the pure polymer electrolytes, they're not likely to be adapted for especially high rate applications. Some of these gel polymer electrolytes are already in use in commercial cells, but they still have a lot of the same disadvantages of the liquid systems. This brings us to the last topic, which are inorganic solid electrolytes. So there's been a big push, especially in the last 10 years, we'll say, on investigating ceramic inorganic solids as electrolytes for lithium batteries. And as you can see from this plot here, compared to the liquid standard EC-DMC electrolyte, which has a very high conductivity over a pretty broad temperature range, a lot of these inorganic ceramic electrolytes, such as the lithium lanthanide zirconate and also the LGPS solid ceramic electrolytes, have very, very high conductivities. Much higher than the PEO, polyethylene oxide lithium perchlorate, which is a non-gel electrolyte. That's a pure solid electrolyte, pure solid polymer, and also significantly higher than the original ceramic lithium conducting solids such as lipon. So these LGPS and LLZ solid electrolytes, they show significant promise due to the very high conductivities. Once again, with a series of these materials, by modifying these lithiated ceramic species, such as lithoscon and the LGPS species, what you can get is significantly high ionic conductivity of these solids. You can see the whole range by different doping levels, we'll say, by modifying the ratios of these different different metals that are present within the system. You can significantly vary the overall conductivity of these materials and get very, very high and very, very promising lithium ion conductivities for these ceramic inorganic solid materials. And once again, if you compare the lithoscon and the nasicon and the perovskite garnet, once again, we see pretty high ionic conductivities in these ceramic solids. These are normalized ionic conductivities. However, the biggest problem with these ceramic inorganic solids is they've got poor interfacial contact with the electrode materials. And so basically what you're trying to do is to incorporate a solid inorganic solid into a cell where you have already solid cathode materials, lithium cobalt oxide, and anode materials, graphite. And at the same point, it's very hard to get wettability. So these have a very low effective wettability. It's very hard to make good surface contact between the inorganic ceramics, the lithoscon, and the lithium cobalt oxide, especially around the entire particle. If you recall, these cathode particles are basically spherical in nature, and it's very difficult to get the solid inorganic solids down into the pores of the cathode and the anode. While with the liquid electrolyte, you put the liquid electrolyte into the cell, the liquid electrolyte wets the cell. There's very, very high contact with the lithium, with the liquid electrolyte along all of the surfaces of both the cathode materials and the anode materials. And then one of the other problems with the ceramic inorganic solids is you have a lot of cracking upon cycling. So one of the things that I did not mention with both the graphite anodes and with the lithium metal oxide cathode materials is there are small volumetric changes that occur when you incorporate lithium into the graphite or you take lithium out of the lithium cobalt oxide. I mentioned this is a real significant problem with silicon anodes because silicon undergoes a 300% volumetric expansion and contraction. But even in the case of the lithium cobalt oxide and the graphite, we have 5 or 10% volumetric changes of the materials upon incorporation or upon lithiation and delithiation. In a liquid electrolyte formulation, these small volumetric changes are not really a problem. They don't really cause any issues. However, when you go to an all solid state system where you have an all ceramic electrolyte, even these small 5 or 10% volumetric changes of the anode and the cathode during cycling can result in significant cracking of these materials. And these significant cracking in the materials results in significant impedance growth of the cathode or of the electrolyte itself, and even poorer contact with the solid ceramics, with the solid ceramic electrolytes and the electrode materials. And so while there's certainly a lot of interest in going away from liquid electrolytes and going to full solid state systems, especially these solid ceramic electrolytes, there are real large challenges in terms of building real commercial cells with these solid electrolytes. And then the final type of electrolyte that I'd like to touch on is something that was recently developed here in 2015 by Kang Zhu and co-workers at the Army Research Labs, and these are referred to as water in salt electrolytes. So water is a very, very good solvent. However, it's got a very small electrochemical stability window. But what was observed was that if you utilized extremely high concentrations, extremely concentrated, solutions of lithium TFSI in water, 21 molar. So your standard lithium ion battery electrolyte is usually 1 molar in salt. These are 21 molar, so it's 21 times as high salt concentration. By doing this, you significantly expand the electrochemical potential window. So when you start off, water has a relatively low electrochemical potential window between reduction and then oxidation of the cells. However, when you go to these very, very concentrated water and salt electrolytes, this electrochemical window is expanded very, very significantly. And the reason that this electrochemical window is expanded so significantly is in 21 molar LiTFSI in water, you effectively have no free water. All of your water is bound to the lithium cations that are in the electrolyte. And so under these conditions, basically water is really not present because it's water as a solvated species. And by doing so, this really changes the overall electrochemical properties. So with these water and salt electrolytes, the researchers were able to observe very good electrochemical cycling performance. And you know, there are a lot of challenges that remain with these systems, especially related to high viscosity and also very high cost, because these salts, the lithium salts, are typically the more expensive component of the electrolyte as opposed to the solvents. So if you go to very, very high concentrations of salt, you're going to result in very, very large increases in the overall cost. However, these water and salt electrolytes are really very novel, very interesting, and very promising in terms of developing novel electrolyte formulations for the future. At the same point, there are also a significant interest in other very concentrated electrolytes where you use very high concentrations of salts and other solvents such as phosphates or carbonates. And there's also been significant interest in very, very useful novel properties that have been observed. And once again, for the same reason, because you're basically binding all of the solvent to the lithium salts, and you're changing the electrochemical properties of the electrolyte via that strong binding. And so, in summary here, the critical components of the electrolyte are, first off, excellent conductivity. You need to have good interfacial properties. Also very good stability, both thermal stability and electrochemical stability. They need to be safe and also non-toxic. You also need them to be inexpensive, since this basically is, these are inherently commercially viable problems that need to be solved. And at this time still, the LiPF6 in ethylene carbonate with various other components, typically dialkyl carbonates, along with electrolyte additives, is still the best electrolyte formulation for most properties. And so in that context, once again, thank you for listening to this presentation. And we have 2 additional lectures coming up forward. One which will be focused on the reactions of the electrolyte with the surface of the anode and the generation of the anode solid electrolyte interface, along with how the anode solid electrolyte interface evolves upon aging and cycling. And then the final lecture in this series will be the reactions of the electrolyte with the cathode and the development of cathode passivation additives to improve the overall performance. And so with that, thank you very much for listening to the lecture.